Hello students, this is your chemistry teacher. Today we are going to discuss the chemistry of group 17 elements. So basically we will be discussing on the following topics today. Occurrence of group 17 elements, variation of ionic radius, ionization energy and electron affinity, oxidation states of these elements and reaction with hydrogen and metal, preparation and properties of chlorine, preparation and properties of hydrogen chloride and oxoacids of chlorine, interhalogen compounds, their preparation and structures. So let's get started. So before coming to the uh, main topic of chemistry of group 17 elements, I would like to give a short introduction about the nature of the group 17 elements. So first of all, group 17 elements are the most electronegative elements in the periodic table. They have the general electronic configuration NH2 NP5. So there are 7 electrons in the outermost cell. Okay, and that's why they are just one electron short from the nearest noble gas configuration, and for this reason they have the strong tendency to accept one electron and to reach the nearest noble gas configuration. For this reason they are considered as the most electronegative element in the periodic table. Okay, so in the group 17 elements we will be discussing on the elements fluorine, chlorine, bromine, iodine and astatine. These are the 5 members present in the group 17, and in this slide we will be discussing on their about their source. So first of all, fluorine is obtained in the mineral fluorspar that has the formula CaF2, calcium fluoride. It's called fluorspar. Okay, chlorine is mainly obtained in the mineral like cryolite that has the formula Na3AlF6, rock salt NaCl, potassium chloride. These are the main sources of chlorine. Bromine is mainly found in bromides present in seawater. Iodine is mainly found in sodium iodate NaIO3 and seaweeds. In the seaweeds also we could find iodine atom. Astatine is a radioactive element mainly, and basically astatine is found as the it is found when radioactive element, if we take our radioactive element and if we follow the process of spontaneous decay of that radioactive element, we could find astatine. So astatine has the source of radioactive element. Okay, now we are going to discuss the variation of atomic radius, ionization enthalpy, electron gain enthalpy for these 5 elements in group 17. Okay, so first of all, as you can see that fluorine to astatine, the size is continuously increasing from top to bottom. From fluorine to astatine, the size is increasing. Due to this reason, atomic radii increases from fluorine to iodine down the group. Moreover, one thing is important to observe here, that halogens are the elements of smallest atomic radii in their respective periods, because as we know, the halogen atoms are present in the extreme right positions of the periodic table, and as we know, from left to right the size of the elements decreases, right? So obviously these elements are going to be the smallest elements present in the periodic table, right? So, and for this group 17, from fluorine to astatine, size of the elements are increasing because of the introduction of new cell in the elements. The size of the elements are increasing from fluorine to astatine. Now, as the size of the elements are increasing from fluorine to astatine, we can expect that ionization enthalpy of the elements are getting decreased from top to bottom, from fluorine to astatine or from fluorine to iodine. Ionization enthalpy decreases because the size is increasing from fluorine to iodine or from fluorine to astatine. So consequently ionization enthalpy will decrease, right? Now the most important variation or property for the group 17 element that we have to look on is the variation of electron gain enthalpy or the variation of electron affinity. So as we have already discussed that electron gain enthalpy or electron affinity generally are of negative values. They have electron gain enthalpy values or electron affinity values are generally negative values. Why they are negative, I have already discussed in previous videos, right? Now as we are saying that fluorine, chlorine, bromine, iodine, astatine, these elements will have the greatest tendency to accept electron because of the electronegativity nature of these elements. So obviously we can expect they will have the maximum negative electron gain enthalpy values, right? So they halogen atoms are the atoms or are the elements having the maximum negative electron gain enthalpy values. Now I have shown some electron gain enthalpy values here. As you can see that for all halogen atoms, fluorine, chlorine, bromine and iodine, electron gain enthalpy values are negative. And basically when the size is increasing from fluorine to iodine, obviously the tendency to take electron or tendency to hold electron in the outermost orbit or tendency to accept electron in the outermost orbit will decrease. So electron gain enthalpy value will be decreased. That means the as we move from fluorine to iodine, the electron gain enthalpy values become less negative, right? So here you can just realize this fact by observing the values of electron gain enthalpy from fluorine to iodine. From fluorine to iodine, the electron gain enthalpy values are becoming less negative, minus 33, minus 303, and the last value is minus 295. That means the values are getting less negative, and this is due to the increase of size from fluorine to iodine. But here one thing is very important to observe here, that fluorine and chlorine, uh, electron gain enthalpy values are getting less negative. That means chlorine must possesses less electron gain enthalpy than fluorine, but here there is an anomalous behavior, there is an anomalous value that we are observing right now. Fluorine should have greater ionization enthalpy than chlorine, but ionization greater electron gain enthalpy than chlorine, but electron gain enthalpy of chlorine is higher than fluorine. Okay, so this is anomalous data of electron gain enthalpy for fluorine and chlorine. Okay, so this anomalous data of electron gain enthalpy of fluorine and chlorine is due to a particular reason. The reason is, as we know, fluorine is the smallest size atom. We can say that the fluorine is the element of uh, highest charge by radius ratio, uh, because charge by radius, if radius decreases, charge by radius ratio increases. That means fluorine will have the highest charge density. Okay, charge density means charge by radius ratio. So fluorine will have the highest charge by radius ratio. That means fluorine will have the highest charge density. The charge is very much dense in fluorine atom due to the smallest size of fluorine. So as since the fluorine will have the highest charge density, it's very difficult for the fluorine atom to accept one electron from outside, because charge density is already high in fluorine atom. So tendency to accept one electron from outside will be less in fluorine atom, and that's why electron gain enthalpy values is less compared to electron gain enthalpy values of chlorine. Okay, and this is the reason why fluorine will show less electron gain enthalpy value than chlorine. Okay, now let's move on to the next topic, that is oxidation state reaction with hydrogen and metals. So what are the oxidation states possible for these halogen atoms? Halogen atoms generally possesses oxidation state from -1 to +7, where -1 oxidation state is only shown by fluorine atom. Okay, fluorine is the most electronegative element in the periodic table, and that's why fluorine has the oxidation state only one oxidation state. Fluorine possesses only one oxidation state, that is -1. But for the rest element, chlorine, bromine, iodine, the oxidation state ranges from -1 to +7. As I have shown some compounds where you can see the different oxidation states of the elements of the halogens in different compounds. Suppose in the compound Cl2O, chlorine will have the oxidation state +1. In ClO2 it is +4. In Cl2O6, chlorine have the oxidation state, chlorine has the oxidation state +3. In BrO2, bromine has the oxidation state +4, and consequently iodine is +5 in I2O5, +7 in I2O7, and chlorine and bromine will have the oxidation state -1 in the compound HCl and HBr. Okay, so these are the different oxidation states in different compounds of the halogen atoms. Now let's discuss the and the compounds what are mainly let's discuss the hydrides of group 17 elements. These are the hydrides of group 17 elements: HF, HCl, HBr and HI: hydrofluoric acid, hydrochloric acid, hydrobromic acid and hydroiodic acid. So if the hydrides of group 17 elements, if we consider, then thermal stability, if we discuss the variation of thermal stability of these hydrides, thermal stability decreases from HF to HI. And this is obvious, no, because as we move from fluorine to iodine, the size of the element increases from fluorine to iodine, right? And that's why the bond, this bond HM bond, where M represents the group 17 elements, HM bond length increases, consequently bond strength decreases, and consequently thermal stability also decreases from HF to HI, because size is increasing from fluorine to iodine. And that's why the HX bond or HM bond, where M represents the fluorine, chlorine, bromine and iodine, HM bond is getting longer, bond strength is getting less, and that's why thermal stability decreases from HF to HI. Now acidic strength consequently increases from HF to HI. Why? Because for the same reason, from fluorine to iodine, size is increasing, and that's why HM bond, where M represents the fluorine, chlorine, bromine and iodine atom, the HM bond is becoming longer, and that's why bond strength is becoming weaker, and that's why the hydrogen atom can easily escape from the bond, can easily escape from the compound easily in the form of proton. And that's why when we move from HF to HI, acidic strength increases. Now let's discuss the uh, compounds where halogen atoms are making compounds with metals. Okay, these are the compounds MF, MCl, MBr and Mi, where M represents metal. Okay, these are the compounds where fluorine, chlorine, bromine and iodines are making some compounds with metal. Now as you can see, as I have demonstrated here, that covalent character of these compounds MF, MCl, MBr and Mi increases from MF to Mi. Why is it happening? It is happening because in this compound, if you carefully observe one thing, in these four compounds the cation is common, M plus cation is common. Only the anion is different. Here the anion is F minus, here it is Cl minus, here it is Br minus, here it is I minus. So as we have learned in class 11 from Fajan's rule, that larger the size of the anion, larger will be the neutralization of the larger will be the neutralization between the cation and anion, and larger will be the covalent character of the compound. As you can see over here, that cation is common, so we are not bothered about the cation, we are interested about the anion. What are the anions? F minus, Cl minus, Br minus and I minus, and the size of the anion is getting increased from F minus to I minus. As the size increases, the neutralization between the M plus and X minus, or neutralization between the cation and anion, increases, covalent character increases. That's why MF to Mi covalent character is increasing. Now if we just highlight two compounds, where one compound is SnCl4 and another compound is SnCl2, and if I ask all of you a question, that who will possesses greater covalent character, SnCl4 or it is SnCl2, who will predominantly show the covalent character? So first of all, we have to look on the cation and anion which are present in this compound. In this compound, cation is Sn4 plus, anion is Cl minus. In this compound, cation is Sn2 plus, anion is Cl minus. So as we know, the higher the charge of the cation, higher will be the neutralization between the cation and anion, and higher will be the covalent character of the compound. So obviously the tin4 plus will be more neutralized by Cl minus than tin2 plus. This is obvious, right? Tin4 plus will be more neutralized by Cl minus than tin2 plus, and that's why SnCl4 will possesses higher covalent character than SnCl2. Okay, now so this is all about these oxidation states and reaction with hydrogen and metals. Now let's move on to the next topics. So preparation and properties of chlorine. Now let's firstly discuss the preparation of chlorine. So first of all, what is the industrial method of preparation of chlorine? So in industry, chlorine gas is being is prepared by treating a mixture of solid NaCl, manganese dioxide and concentrate H2SO4. Okay, as you can see over here, if we mix this NaCl solution with manganese dioxide and concentrate H2SO4, and if we heat the mixture, we can get the chlorine gas as a major product. Along with the along with this chlorine gas, there would be some byproduct formed. These are sodium bisulfite, NaHSO4, manganese sulfate, MnSO4 and water. What is now let's move on to the Decon's method of preparation of chlorine. In the Decon's method of preparation of chlorine, what is going to happen? The hydrogen chloride is oxidized in presence of a catalyst cuprous chloride CuCl2, where hydrogen chloride will be oxidized by O2 to give chlorine Cl2 gas as a major product with the liberation of water. Now, what are the properties of chlorine? So first of all, let's discuss the properties one by one. The first property is reaction with base like NaOH. So what is going to happen when chlorine gas will react with NaOH solution, mainly cold dilute NaOH solution, a mixture of sodium chloride and sodium hypochlorite is obtained. This reaction is very much important for board exam. Maximum times it used to come in this way. What happens when chlorine reacts with cold dilute NaOH? Okay, so chlorine is basically reacting with cold dilute NaOH, and it is giving you a mixture of sodium chloride NaCl and sodium hypochlorite NaOCl with the liberation of water. Secondly, when chlorine reacts with hot and concentrated NaOH solution, then a different product is obtained. The product is a mixture of sodium chloride and sodium chlorate. Okay, this is a slight difference you have to look on. Here chlorine is reacting with cold dilute NaOH to give a mixture of NaCl and NaOCl. Here the chlorine is reacting with hot and concentrated NaOH to give you a mixture of NaCl and sodium chlorate, NaClO3. Okay, now the reaction of chlorine with calcium hydroxide base. So calcium hydroxide is used to calcium hydroxide when reacts with chlorine gas, it gives bleaching powder CaOCl2 as the major product with the byproduct CaCl2 and water. Okay, now the most important property of chlorine is the bleaching property, bleaching nature or oxidizing nature of chlorine. So first of all, why the and how the oxidizing property of chlorine appear in the chlorine molecule, right? So first of all, when chlorine water, if we are allowed to stand the chlorine water for long time, okay, if we allow to stand a chlorine solution, chlorine water solution or chlorine water for long time, it will give you a mixture of HCl and HOCl, hydrochloric acid and HOCl. This HOCl that is so formed from spontaneous decomposition of chlorine water will give you HCl and the nascent oxygen atom. As we have already discussed, this nascent oxygen atom is very much effective to oxidize other species effectively, and that's why the nascent oxygen that is so produced from chlorine water is capable to oxidize the iron 2 plus, okay, or to oxidize any compound. Here I have shown the oxidation reaction with iron 2 plus and chlorine water, where nascent oxygen of chlorine water will oxidize the iron 2 plus to iron 3 plus, and chlorine will be itself reduced to Cl minus. Okay, so the question is used to come in this way, that write the bleaching action and the oxidizing nature of chlorine. Who is responsible for the bleaching action of chlorine, or who is responsible for the oxidizing nature of chlorine? So these are the reactions. Okay, the reason is nascent oxygen, and you have to give one reaction, iron 2 plus plus chlorine Cl2 plus, in presence of H plus, the iron 2 plus will be oxidized to iron 3 plus and chlorine will be reduced to Cl minus. Now let's move on to the preparation and properties of hydrogen chloride and the oxo acids of chlorine. The first of all, hydrogen chloride, we have to discuss the hydrogen chloride preparation. Hydrogen chloride is basically prepared by treating NaCl with concentrated H2SO4, where in the first step NaCl is going to react with H2SO4 and it will give you NaHSO4 and HCl. Okay, in the second step, the NaHSO4 so formed in the first step will gonna react with NaCl, sodium chloride, and it will give you Na2SO4 and HCl. Okay, now what are the properties of HCl? So first of all, in gas state it has covalent nature, whether in aqueous solution it behaves as acid. Okay, hydrogen chloride that we used to talk about every time is a covalent compound in the gas state. Okay, in the gas state it has a covalent nature, hydrogen chloride, then it is termed as hydrogen chloride. When hydrogen chloride is taken in water, then in presence of water the hydrogen cation and chlorine anion will be separated in the form of H plus and Cl minus. Then we can say hydrogen chloride act as an acid, that is called hydrochloric acid. Okay, so in gaseous state hydrogen the molecule is hydrogen chloride and it has a covalent nature. In aqueous solution, that means in when it is taken in water, the hydrogen chloride will spontaneously will be decomposed into H plus and Cl minus. Then hydrogen chloride will act as an acid in aqueous solution, not in the gaseous state. Now if we take a mixture of hydrochloric acid, concentrated hydrochloric acid, and mixture of concentrated hydrochloric acid and concentrated HNO3 in the ratio of 3:1, if we mix them in the ratio 3:1, then we will give we will get a solution that is called aqua regia. Okay, aqua regia is mainly obtained by mixing 3 moles of hydrochloric acid and 1 mole of concentrated HNO3. Okay, and this aqua regia is very much effective to oxidize or to dissolve some undissolved substances. There are some substances which are not going to dissolve in any solvent. In that case we use aqua regia as a solvent. Okay, this aqua regia can easily dissolve those compounds in the medium. Now metals react with hydrochloric acid. In the third property, metals react with hydrochloric acid or HCl to liberate hydrogen. That is a very simple reaction where metal iron is reacting with hydrochloric acid HCl to give you the salt ferrous chloride FeCl2 with the liberation of hydrogen H2. Okay, now let's discuss the most important part of this chapter, that the oxoacids of chlorine. There are mainly 4 oxoacids of chlorine that are very stable. Which are they? They are hypochlorous acid HOCl, chlorous acid HClO2, chloric acid HClO3. This is the structure of HClO3, and perchloric acid HClO4. As you can see in the first compound HOCl, there is only one electronegative element, chlorine, that is attached to oxygen atom. That's why the electron deficiency of oxygen atom is very less, and that's why the tendency for this hydrogen to escape from the by breaking the bond in this way is very much less, and that's why the acidity of this hypochlorous acid is very less. Okay, moreover, if we consider the rest oxoacids of chlorine as HOCl, HClO2, HClO3 and HClO4, where chlorine is the number of double bonded oxygen atom in the first compound is 1, in the second compound 2 double bonded oxygen atoms are there, and in the third 3 double bonded oxygen atoms are there, right? So as the number of double bonded oxygen atom increases from chlorous acid to chloric acid to perchloric acid, the electron deficiency on the chlorine atom increases due to the presence of the double bonded oxygen atom attached to the chlorine atom. Okay, so as the number of double bonded oxygen atom increases from left to right, the electron deficiency is increasing from on the chlorine atom from left to right. And as the electron deficiency increases, the eventually the electron deficiency also increases on the oxygen atom from left to right. If chlorine is getting electron deficient from left to right, oxygen will also be electron deficient from left to right, because oxygen is directly attached with chlorine, right? So electron deficiency on oxygen atom increases from left to right. So as the electron deficiency on oxygen atom increases, the hydrogen atom will break this OH bond in this way, and it will escape from the compound from left to right. The tendency to escape the tendency for the hydrogens to be escaped from these compounds increases from left to right, because from left to right oxygen is getting more and more electron deficient from left to right, right? So that's why the tendency to leave the compound for the hydrogen atoms, for these hydrogen atoms, increases by breaking the bond in this way, and that's why the acidity increases from left to right. And for these reasons, the overall acidity would be like this, would be the least acidic HOCl, and acidity increases from HClO2, then HClO3, then HClO4. Okay, now let's move on to the most important topic of this chapter, interhalogen compounds, their property, preparations and structures. So what are interhalogen compounds? Interhalogen compounds are the compounds where where two or more same or different halogen atoms are linked by covalent compounds, are linked by covalent bonds, then the compounds formed are called interhalogen compounds. From the name itself, it's clear that interhalogen compounds are formed by the combination of two or more halogen atoms. They may be they might be same, they might be different. Okay, they have the general molecular formula, X dash N, where X and X dash are the halogen atoms. X and X dash can be same, they can be different, and N, this N can be small whole numbers like 1, 2, 3. And if I give you some examples of interhalogen compounds, the examples are like ICl, iodine monochloride, ClF, chlorine monofluoride, ClF3, chlorine trifluoride, I3 minus, ICl2 minus. These are all interhalogen compounds. All are made by the combination of halogen atoms, na? Iodine, chlorine, fluorine. They are combining to form these compounds. Okay, now let's discuss the preparation of interhalogen compounds. They are mainly obtained, as I have already told, that they are mainly obtained by direct combination of halogens or by combination of halogens with simple interhalogen compounds. Here, as you can see, that chlorine and fluorine, they are the simple halogen atoms. They are combining to give ClF. Okay, at the temperature 437 Kelvin. Iodine and chlorine, they are combining to give iodine ICl. Chlorine in reaction with excess fluorine is giving you ClF3. Okay, BrF3 is in combination with fluorine F2 to give you BrF5. ClF3 is combining with F2 to give you ClF5. So here the interhalogen BrF3 is itself a interhalogen compound, and it is reacting with a halogen atom to give you a new interhalogen compound. Here also ClF3 is an interhalogen compound. It is reacting with a halogen atom F2 and giving you a new interhalogen compound ClF5. Okay, so these are some preparations of interhalogen compounds. Now let's discuss the structures of these interhalogen compounds on the basis of VSEPR theory that we have already learnt in class 11. In the first structure, that is the ClF structure, the central chlorine will have 7 electrons. All the halogen atoms have 7 electron in their valence shell, right? So this chlorine atom will have 7 electrons in its valence shell. Okay, and there is only one bond, so plus 1 electron it will get. This extra 1 electron chlorine atom will get by due to the formation of this bond, formation of this sigma bond. Okay, so total 8 electrons chlorine atom will have, right? So 8 electrons means 4 electron pairs. That means 4 electron pair means the structure should have been tetrahedral, but among these 4 electron pair, one is bond pair and 3 are lone pair. So structure should have been tetrahedral, but actually the structure is linear. Now according to the now the applying the same concept of VSEPR theory, we can predict the structures of the rest compounds. Now ClF3, in the central chlorine atom 7 electrons, the chlorine atom is making 3 bonds, so plus 3 electrons due to the formation of 3 bonds, so plus 3, total 10 electrons. 10 electrons means 5 electron pair, so structure should have been trigonal bipyramidal structure. Structure should have been trigonal bipyramidal structure. Okay, if you consider this lone pair, the structure is looking like a trigonal bipyramidal, right? So structure should have been trigonal bipyramidal structure, but among these 5 electron pair, 3 are bond pair and 2 are it will be 3 bond pair and 2 lone pair. This will be 2 lone pair, right? So 3 bond pair and 2 lone pair, and that's why if you just ignore these lone pair, because we know that lone pairs are not going to contribute in the structure of the compound. So the structure is looking like a T shape, looking like a T. So the structure will be T-shaped. Okay, now ICl2 minus. ICl2 minus has the structure like, if I consider the central iodine atom as the central atom, it is the central atom, right? So iodine has 7 electrons in the valence. So here iodine is the central atom, so iodine has 7 electrons. It is making 2 covalent bonds, so plus 2 electrons for 2 making of two bonds and plus one electron for this negative charge. Okay, so total 10 electrons are there for this compound. So 10 electrons means 5 electron pair. So 5 electron pair means the structure should have been trigonal bipyramidal structure. If I consider these lone pairs as substituent, then the structure will be looking like a trigonal bipyramidal structure. But in the among these 5 electron pair, 3 are lone pair. These are the 3 lone pairs that are present in equatorial positions, and 2 are bond pairs. These are the 2 bond pairs. So as we know that these lone pairs are not going to contribute in the main structure, in the actual structure, so the structure will be linear. This you can see this is linear structure, and this is due to these two bonds, right? So the structure should have been trigonal bipyramidal, but due to the presence of 3 lone pair, the structure would be linear. Now let's move on to the next structure, that is the structure of BRF5. So in the structure BRF5, the central atom is bromine, so it will have 7 electrons. For bromine atom, central bromine atom, the structure 7 electrons are there, and there bromine atom is making 5 bonds, 5 covalent bonds, so plus 5, so total 12 electrons. 12 electron means 6 electron pairs. So 6 electron pairs means the structure should have been octahedral, but due to the presence of one lone pair among these 6 electron pair, 5 are bond pair. These are the 5 bond pairs, right? The structure in the structure there are 5 bond pair and one lone pair, and lone pair is not going to contribute in this structure. So the structure will be due to the will be due to these 5 bond pairs. So the structure should have been octahedral, but actual structure is going to be square pyramidal. Okay, so these are the topics of group 17 elements. Hope you have understood all the logics, all the topics. If you have any doubt, you can contact me anytime. Thank you for watching this video. See you in the next class. Thank you.